Okay, so today I'm going to talk about the electrostatic equations. So this will include, for example, Coulomb's force, but also electric field equations and electric potential energy, as well as electric potential. When something has a charge, it automatically and always produces an electric field around it, which is denoted by E. This field attracts opposite charges and repels like charges in the form of a force. It's important to understand that a field is not a force, but it describes the magnitude of potential forces in an environment. It's easier to imagine it like a heat map. For example, if a charge was in this area, in all of these different places, it would experience a higher force than here, 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 or here. So the electric field that's produced by this charge Q is not what is moving Q1 and Q2, but it explains the magnitude of the force that is experienced by Q1 and Q2 at any of these points in space. At this point, it's also good to introduce the notation of proportions. If we have a factor A and B, and they're both directly proportional, we use this symbol. This means that as A increases, so does B, and we get a graph that looks like this. As A increases, so does B. And we say that these values are directly proportional. However, if we see that as A increases, B decreases, or vice versa, we write this. And we end up with a graph that looks like this. As A gets higher, B gets lower. You can draw intersects with the line and confirm this. For this type of relationship, we say they are inversely proportional. That's the same as if writing A is proportional to 1 over B. If we have a relationship that's not directly linear, but instead exponential or logarithmic, then we can also include that in our expression. For example, we can write that A is directly proportional to 1 over B squared. Or we can say that the log of A is directly proportional to B. In school, we often accept equations just as they are without questioning them. But they aren't magical formulas that shouldn't be questioned. In reality, an equation just summarizes multiple of these types of relationships. For example, if variable A is directly proportional to B, and variable A is inversely proportional to C, then we can write that A equals B divided by C. Now we have an equation that explains A in the terms B and C, just based on its relationships. As we go on to understand the electrostatic equations, it's important to keep this in mind. When you see a formula, all it describes are relationships between different factors. And they don't have to be absolute. You can add or remove different factors to create your own formulas. It just depends on what you're trying to describe. A good example are the chemistry gas laws. They are made up of a set of factors, including pressure, volume, and temperature. And they can be mixed around to produce all sorts of different formulas, including one where they are all involved. Let's go back to electric fields. We know that if our charge Q is stronger, then the electric field will also be stronger. Hence we can write that Q is proportional to E, our electric field. We also know that an electric field is strongest near the charge. It gets weaker as you're moving away. Thus we can write that the strength of our electric field is inversely proportional to R, our distance. However, the electric field is not just expanding in 1 or 2 dimensions, but in all 3. It's a sphere after all. So the surface area of a sphere is given by 4 pi r squared. So to be exact, E is actually inversely proportional to 4 pi r squared. This also matches with experimental data. Keep in mind that scientists are always trying to prove their theories through experimental values. And calculations including just r or r cubed just don't hold up the same way that r squared does. Another factor is the permittivity of free space, denoted by epsilon 0. This value that's experimentally found describes how easy it is for an electric field to spread through a vacuum. A smaller permittivity would mean that it is harder for the electric field to spread out. This would mean that it is smaller and hence stronger because you could say it is more concentrated. And a larger permittivity means that the field is more spread out and so weaker because, again, we could say it is less concentrated. So our electric field is inversely proportional to the permittivity of free space. If we put all of these together, we can write that the strength of the electric field is equal to our charge divided by 4 pi r squared times the permittivity of free space. Some of these values are always changing. For example, the strength of our charge can increase or decrease depending on what charge is present, and also the distance is constantly changing depending on where you're approaching the charge from. However, 4 pi is a constant scalar, and so is the permittivity of free space. These values will not change. So instead of clunking up the equation, they can be removed into a constant, k, called Coulomb's constant. So we can rewrite the equation like this, where k is 1 over 4 pi epsilon of 0. And this is it. This is the formula for the strength of an electric field. Given a certain charge q at a certain distance, it will tell you what kind of force you could predict another charge would experience. But remember, it doesn't explain the force itself. It only describes what magnitude of forces are present at what distance given this charge. This is because there is another very important factor in determining the exact force value, and that is the other charge that is present in this field, little q. We can go back to the example of a heat map. A heat map shows the different temperatures in space. For example, here's a hotter temperature, and here's a much cooler temperature. However, the actual temperature that you experience also depends on you. You could be wearing a winter jacket or a summer dress, and these temperatures stop being so objective and start to feel subjective. The same is true in this case. We have a charge, q, that is producing an electric field, and this field is stronger near q and weaker further away. The electric field describes what kind of force you will feel at any point in the space. However, the force that you do end up feeling also depends on your own magnitude. Since q2 is negative, it feels an attractive force, but this force would be much stronger if q was much stronger, and it would be weaker if q was a weaker charge. This attractive force between these two charges increases when both of these charges increase in strength. So clearly the force that is experienced is proportional to q, and it is also proportional to little q, our other charge. And lastly, it's also proportional to the electric field. So we can write that the force is equal to our electric field times little q. And this equals big Q multiplied by small q divided by r squared, and of course, don't forget to multiply by our constant. And this is it. We did it again. This is the formula for the force between two charged particles. This is also called Coulomb's force. You may have noticed that mass, velocity, time, or angles are omitted from this formula. That's because Coulomb's law only describes the electric charges of static particles, so no motion, which would introduce magnetic effects, which are covered by the Maxwell's equation. When you have two charges, the force is always linear between them. However, when you introduce a third, or more charges, now you will have a vector problem. Now each pair of charges is interacting and exerting their own forces on each other. In that case, we will need angles. If you're doing a physics problem and also want to include the gravitational force, then you may also wish to include mass. So again, these formulas are not untouchable. They're malleable, and they can be changed in any way that fits you. Moving on, we're going to get into a tricky area regarding the naming. There are two very important formulas that give you the electric potential and electric potential energy. These are not the same. Please do not mistake these for each other. However, I think it's going to be quite a long video because I'm going to be covering a lot of different topics in physics such as work, energy, potential energy, kinetic energy, and even integration. So first, before we move on to the next section, I really advise anyone who doesn't know what integration or calculus is to look up on it. Also, having a solid understanding of work and the different types of energies would be really helpful, because I'm going to get quite conceptual and formal with the definitions, and it can get a little bit confusing, but trust me, once you really understand it, it really pays off. It's very satisfying to truly intuitively understand these concepts. But that being said, I am going to post it as a separate video because I think it's going to be quite a long video. So if you're brave enough, I hope to see you there.